2.3, inverses of matrices. Okay, a matrix has to be square to be invertible. So an n by n matrix, we'll call it A, is invertible if there exists another matrix, same size, such that the product equals the identity. In other words, AB equals identity, or BA equals the identity. This is one case in which multiplication will be commutative. Normally it is not. You've shown that. Okay, so in this case we say that A is the inverse. Note the -1 superscript, not an exponent. This does not mean division. It's an operator, a superscript that says the inverse, just like arcsine or something like that. The -1 is not an exponent. And we say that B is the inverse of A. Inverses of matrices are unique. There's only one inverse to an invertible matrix. Unique. Okay? Now, let's show this. An example, let's say I have A is the matrix -1, 2, 4, 1. And B is the matrix, this is ugly, -1/9, 2/9, 4/9, 1/9. I know they look similar, but don't think that you can find a shortcut. There is a shortcut, but I don't recommend it. It only works for 2x2 matrix inverse problems, which doesn't serve you well because you're going to need to know how to find an inverse of any size square matrix. I'm going to rewrite B by pulling out the 1/9. Remember scalar multiplication. If it works to multiply it through, then you can unmultiply it, right? Makes our work a lot easier here. And also the properties of scalar multiplication being commutative shows me that when I multiply A times B, I can pull that 1/9 out front. And A times B, oh look, they're the same. Huh. But they're not exactly the same. So I have 1/9 here. When I multiply, remember you go across and down. So -1 minus 1 is 1. 2 times 4 is 8. You see that gives me a 9 there. Row 1 times column 2 gives me -2 plus 2. There's a 0. Second row, 4 times -1 and 1 times +4. Column 2, 4 times 2 plus 1 times 1. And you see I have 1/9 times 9009. And that is the identity matrix in a 2x2. If you multiply them the other way, you're going to get the same answer, obviously, because the 1/9 factored out means it's those two things are the same. Okay. All right. Now, how do you find the inverse of a matrix? The book gives you two ways to do it. The first way they show is a complete waste of time. I didn't say that out loud. So we're going to demonstrate here. I'm going to use A again. I'm going to find A inverse if A is what we started with. Sorry about that. If A is -1, 2, 4, and 1. Here's the best way to do it. No matter what size your matrix is, you want to take your matrix, I'll write this down on the next page, augment it with the identity, and then use your row operations to convert the left-hand side into the identity, and then your right-hand side will be the inverse of what you started with. So I'm going to multiply row 1 by 4, add it to row 2, and I want the 0 in the first column to be in the bottom. So I'm going to replace row 2 with that. So I have -4, 8, 4, and 0. That's row 1. Row 2 is the same. Combine those rows, 0, 9, 4, and 1. And that replaces row 2. Row 1 stays the same. And now instead of dividing through by a 9 and getting fractions, I'm pretty lazy and that's messy. So I'm going to leave the 9 and use it. I'm going to multiply row 1 by a -9 and a row 2 by 2. That'll give me a -18 and a +18. I'm going to replace row 1, and then I'm going to go back and divide by whatever I need to divide by to get the ones. So busy work here. -9 row 1s gives me 9, -18, -9, and a 0. Double row 2 gives me 0, 18, 8, and 2. Combine, I get 9, 0, a -1, and a 2. That's my new row 1, sorry. 9, 0, 0, 9, augmented with -1, 2, and row 2 was 4 and 1. And now I'm going to take row 1 divided by 9, replace row 1, row 2 divided by 9, replace row 2, and now I have the identity augmented with -1 over 9, 2 over 9, 4 over 9, and 1 over 9. And that is A inverse. And you can pull out the 1 over 9 if you like. It would be equivalent. And ta-da. And the way you check your answer is you take your answer here, multiply it times the original, and make sure that you get the identity. So always check your work. Okay, to find the inverse, you're going to augment with the identity, same size. Use Gauss-Jordan. That's what we just did. Elimination. To get the identity on the left. The right will be, wow, I can't spell. Look at me. The right will be A inverse. I'm going to call this matrix A. Okay, you check it by multiplying and make sure when you multiply you get the identity. There you go. There's your directions. Let's try another. Since we're lacking space here, let's do another 2 by 2 example. Let's let A be the matrix 2, minus 3, 1, and 4. I want to find A inverse, so I'm going to augment A with the 2 by 2 identity. Now, first thing I want to do is get a 0. All of the problems we've done before have been lower echelon. In other words, we get the zeros in the first column, second row. But we can also get the first 0 in the row 1 in the second column, as long as we don't get a 0 on the diagonal. Now remember, you can invert these rows. They can trade places, because if you think about solving a system of equations, does it matter which equation is the first one and which equation is the second? It doesn't, as long as you keep the equation intact when you switch places. So I could make row 1 be row 2 and row 2 be row 1. It doesn't matter, which means that getting it in row echelon form, it doesn't matter if I do it to the top or the bottom, or the top right or the bottom left. So I'm going to choose the easiest thing and use that minus sign right there to get a 0 in this column. And if I have a 0 in column 2, I want it to be in row 1. I have that freedom. So I'm going to multiply row 1 by 4 and combine it with 3 times row 2. And I'm going to replace row 1. Writing my busy work here, 4 times row 1 gives me 8, negative 12, 4, and 0. 3 times row 2 gives me 3, 12, 0, and 3. Combine those, and I'm going to get 11 and 0, and a 4 and a 3. So that's my new row 1. 11, 0, 4, 3. Copy row 2 as it was. And now I have a choice. I can divide everything by 11 to make that a 1. And then I can use that to eliminate the guy in the bottom. Or I can multiply the bottom by negative 11 and eliminate and get that second 0 and not have to deal with fractions. So because I said I'm lazy, right? That's what I choose to do. So I'm going to have row 1 and a negative 11 row 2 and replace row 2 with that. Busy work gives me 11, 0, 4, 3, that's row 1. Negative 11 row 2, is negative 11, negative 44, sorry about that, 0, and negative 11. And when I combine these guys, I get a 0 where I want it. I can divide away the negative 44 whenever I feel like it. This is a 4, and this is a negative 8. That's my new row 2. Row 1 is still this, and now I'm just going to divide everybody by what I need to divide by. I'm going to say row 1 over 11, replace it. I'm going to say row 2 over minus 44, replace that. And I'm also going to reduce fractions as I go. So in the top row I get 1, 0. In the bottom I get 0, 1, the identity. So I'm dividing row 1 by 11. And I'm going to divide row 2 by negative 44. So 4 divided by negative 44 is going to be minus 1 over 11. 8 divided by negative 8 divided by negative 44 gives me positive 2 over 11. And A inverse will be, I'm going to pull out the 1 over 11, make it pretty. I have 4, 3, -1, and a 2. And that's my A inverse. And then, of course, you always check it when you're done. So I'm going to shrink this down a little and do some checking with a different color here. So A inverse times A, it doesn't matter which one comes first, 4, 3, -1, and 2. Multiplying A to -3, 1, and 4. Multiplying the top row by the first column gives me 8 plus 3 is 11. Second column gives me -12 plus 12. Second row, first column gives me -2 plus 2. Second row, second column gives me +3 plus 8, +11. Distribute that fraction, 1, 0, 0, 1, and it checks out. Good on you. Now let's try a 3 by 3. Okay, these can get hairy. I'm going to thin out my ink here because I'm going to need to write smaller. Let's start with A is 1, 0, 3, -2, 1, 1, 4, -1, 0. And I want to find the inverse. So I take my guy, augment with the 3 by 3 identity. 1 on the diagonals, zeros everywhere else. And now, anytime you're using Gauss-Jordan elimination, please, please, please remember that the first thing you need to do is get 2 zeros in a column. The book will tell you it has to be column 1 and it has to be row 2 and 3. Some books will tell you you could also do column 3, but it would have to be in the first 2 rows. You could also get zeros, 2 zeros in the middle column, 1 on the top and 1 on the bottom. When you're using a computer, though, you're programming your computer to do it for you, then you would always want to do row echelon with the left, lower row echelon form. So you'd have 2 zeros in column 1 at the bottom, and then you would get that third 0 in row 3 in column 2. But it's not set in stone. The final form is what matters, but programming a computer, you don't care how nasty the numbers are, right? So if you're writing the program, the first thing you do is get ones on the diagonal. You divide. Now, ours are all ones except for that 0. That 0 on the diagonal is going to go away when we start doing our row operations anyway. So it doesn't really matter. Very technical type teacher or textbook would tell you that you need to switch row 2 and row 3, and that would automatically give you ones on the diagonal, but it doesn't matter because we're going to be adding and multiplying and combining and things like that, so we're going to lose those guys anyway. So I'm going to focus on doing it the way they say to do it and get 2 zeros in column 1. So let's start with the bottom number. I'm going to take twice row 2 plus row 3, and I'm going to replace row 3. And here's my busy work. Twice row 2 gives me -4, 2, 2, 0, 2, 0. Row 3 gets copied the way it is. When I combine those guys, I get a new row 3. 0, 1, 2, 0, 2, 1. So my new row 3 is 0, 1, 2, 0, 2, 1. And row 2 stayed the same. Row 1 stays the same. We're going to deal with him at the very end. And that 0 is going to be nice because he's already there. Now I'm going to use the first 2 rows to get the second 0 in column 1. So 2 row 1 plus row 2, and I'm going to replace row 2. Busy work gives twice row 1 is 2, 0, 6, 2, 0, 0. And copy row 2 as it is. I get 0, 1, 7, 2, 1, 0. That is my new row 2. 0, 1, 7, 2, 1, 0. Row 3 stayed the same. This is a lot of writing, isn't it? 1, 0, 3. Be careful that you copy things down correctly. Don't lose any minus signs in the process. So now what I'll need for you to see is when you get zeros in the first column, you've got a 2 by 2 right here. You know how to do this. I need to get another 0 right there. That's going to give me a single non-zero value in this whole row. I can use this guy to get zeros here and here. And the 0 that will be here will not change these 2 pieces. And I'll be almost done. All right, so here we go. Getting a 0 right there, I'm going to multiply row, I'm going to do row 2 minus row 3. Simple enough. Remember, you don't subtract. You always multiply through by a minus and then combine. So row 2 as it is, 0, 1, 7, 2, 1, 0. And multiply a negative through row 3, 0, negative 2, negative 1. Combine, I get a 0 and a 5. This is a 2 minus 1 minus 1. That is my new row 3. 0, 0, 5. And I can just go through and divide by 5 whenever I'm ready. I don't like having fractions on the right-hand side until I absolutely have to, because fractions are like your mother-in-law. If you have to deal with her, you love her to death. But if you can avoid her till the very end, that's even better, right? Those of you with a mother-in-law know what I'm talking about. We won't talk about it out loud though, right? Okay, we now have lower row echelon form, which means that we have this tool right here to get rid of this and get rid of this, and those zeros will keep this piece the same. And because I already had a 0 there, that's already fitting the identity. I only have to do 2 more processes. Now, if that wasn't originally a 0, then once I use this 5 to get rid of that 7, I'll have a value here with 2 zeros in that row, and I would use that to get that 0. But I don't have to. Yay! So I'm going to multiply, instead of dividing through by a 5 and getting fractions, remember I'm lazy, I'm going to do, if you don't mind, 2 processes at once. I'm going to use this 5 to get rid of the 7, and that means I'm going to have a minus 5 row 2 combined with row 3 to replace row 2. And I'm going to do a minus, hold on, I need a 7 there. Erasing this. Minus 5 row 2 plus 7 row 3, big numbers, and replace row 2. And I'm going to get minus 5 row 1, let me erase, minus 5 row 1 plus 3 row 3, and replace row 1. So two things at once. I'm going to do my busy work first. Negative 5 row 1 gives me minus 5, 0, minus, that's minus, sorry, I'm supposed to be doing row 2. Here we go again. Minus 5 row 2 gives me 0, negative 5, negative 35, negative 5 times 2, negative 5 times 1, and anything times 0. And now adding 7 row 3s, that gives me a 0, a 0, a 35. Taking the 7 over on the right, minus 7, combine, I get 0, negative 5, 0, which is what I wanted. This is a 4, a negative 12, and a negative 7. That's my new row 2. Now row 3 is going to stay the same. Just cleaning up here as I go. Row 2 is 0 minus 5. I'll divide in a minute. This is 4, negative 12, negative 7. Now I'm going to do this next process and then write down row 1. So using minus 5 row 1 is negative 5, 0, negative 15, negative 5, 0, 0. 3 row 3 is 0, 0, 15, 6 minus 3 minus 3. Combine, negative 5, 0, 0. I get a 1, negative 3, negative 3. That's my new row 1. And you see, all I have to do is divide by 5s and a couple of minuses. 1, negative 3, negative 3. So my last step is going to be row 1 divided by minus 5, row 2 divided by minus 5, replacing row 2, and row 3 divided by 5, positive, replacing row 3, and I'm going to get 1, 0, 0, 0, 1, 0, and 0, 0, 1, the identity on the left. Now, row 1 divided by negative 5 is going to be minus 1/5, positive 3/5, positive 3/5. Row 2 divided by negative 5 is minus 4 over 5, positive 12 over 5, positive 7 over 5. Dividing row 3 by a positive 5, I get 2/5, negative 1/5, negative 1/5. And now I'm going to pull out the minus 5 when I write down my, a positive 1/5, you know what I mean, when I write down my answer. And I get A inverse equals 1/5 times just the numerators. Minus 1, 3, 3, minus 4, 12, 7, 2, minus 1, and minus 1. And there is my inverse. Now, once you get your inverse, you know that you always check it. So you're going to want to multiply that by the original, make sure that you get the identity, and don't forget you've got that 1/5 sticking out front. Okay, so I know some of you are asking yourselves, what's the point of all this? And I'm finding an inverse matrix is actually one of the most useful things that you can do if you're dealing with large systems. And systems can be used for so many different applications in the real world. If you doubt it, just look through the word problems in any of the sections or some of the application um, sections that where we maybe won't cover, but it's very, very useful. So just one quick thing that we will be doing on the test as a use for this. In the beginning, of the chapter 1, we looked at systems of equations, linear equations, and let's consider this system right here. Now that we know how to multiply two matrices, I can make this make sense. I think I showed it to you in a previous video, but now we have a way to solve a matrix equation. And now before, I told you there's no such thing as matrix division, and there isn't. And I told you that you can't just cancel. Well, there's a little bit blurb in this section in your book that shows you that you can cancel. And I want you to scribble that out because it's misleading, okay? You're not really canceling a factor. You're multiplying by both sides of the equal sign by the inverse of that factor, and that turns it into the identity. And there's actually a big difference between that and quote unquote canceling. So in a system like this, if you want to use matrices to solve, then you can look at the coefficient matrix 2, -1, 1, 1, 4, -3, -1, 2, 2, and then multiply the coefficient matrix by their column matrix x1, x2, x3. Now, if you do that, going across a row and down a column, you see that you have 2x1 minus x2 plus x3. Well, that's this equation 1, and that equals -1. Multiplying row 2 times the column is going to give you equation 2, and that answer is 5. Row 3 times the column gives you equation 3, and that answer is 8. And what you have here is a matrix equation where you have matrix A. We're going to call this coefficient matrix the matrix A. And the variable column matrix we're going to call X. And we're going to show that that equals those parameters over there on the B. Now, we can't just divide both sides by matrix A to isolate the matrix X and show that those x1, x2, x3 are equivalent to what we get on the right-hand side. But what we can do is multiply both sides of this matrix equation by the inverse of A. But remember, multiplication is associative. And A inverse times A is the identity. And if you multiply the identity by the X column matrix, you just get X. A inverse times B, well, A is a 3 by 3, so A inverse is a 3 by 3. We multiply a 3 by 3 by a 3 by 1, and we're going to get a 3 by 1. So you see that the column matrix with the variables will equal a new column matrix, and we can match up because they're exactly the same. Then we can say x1 equals the guy in the top, x2 is the next one, and x3 is the bottom. So that's the way you use an inverse matrix to solve a system. And anytime you have a situation where you have multiplication of matrices, and there's variables in there that you need to solve for, you can just find the inverse and multiply through. Why is that good? Because I've lost my train of thought. I'm sorry, right in the middle of the video. Why is that good? Because in the real world, there may be instances where all of these coefficients, all the coefficients of these different variables maybe represent the importance or the weight or the power or whatever of each of these elements in that situation, like traffic at a stop sign or at an intersection, sorry. The traffic at an intersection is dependent upon the time of day, the day of the week, the weather, whether it's a holiday, the time of year, because the sun may be in your eyes if you're sitting at a traffic light after between this hour and that hour and during these dates. And that's going to change the safety level at that intersection on those days. Just all kinds of things can affect any situation in a real world. But these parameters over here on the right, all of these things carry the same importance forever and ever, but these parameters may change. So instead of using different numbers here and solving the system every single time you change these parameters, you can just find the inverse of that matrix, right? And whatever this B is, the B will change, A inverse will not. And all you have to do is multiply matrices, multiply, 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 and you can get every single answer, boom, 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 without having to resolve your system over and over and over again. So now that I've given you that long-winded explanation, I'm going to erase what I wrote, and we're going to find A inverse and show you how to solve for x1, x2, and x3. All right, hopefully my eraser is big enough to do this. Sometimes my eraser's big and sometimes it's little and I can't figure out how to. I know there's a way to block this out and just erase it, but too lazy to learn how to use my app here. I had a professor that never erased very well, and the board always looked like it was covered with minus signs, and it made for lots of mistakes on everyone's part. So there we go. Let's do this thing. I want to find the inverse of my coefficient matrix. 2, minus 1, 1, 1, 4, and negative 3. And since we've got one of these under our belts already, I may take it upon myself here to do more than one step at once. The book will tell you you need to write down the entire matrix before you do a second step. But if things don't change, then you can just use the original and go for it. So I want to get two zeros in a column. And because this minus 1 and these are both positive, it's going to be really easy to get 2 zeros in column 1. Never, ever, ever start by getting 2 zeros in a row. You're wasting time. You're going to lose one of those zeros when you do more row operations. You want to get it 2 zeros in a column. So I'm going to choose to do row 1 plus twice row 3. I'm going to do that second though, so hold the phone here. I'm going to do row 1 plus twice row 3 and replace row 3. But I'm also going to do row 2 plus row 3 and replace row 2. I'm going to do that first, not that it matters because I know the outcome, but just so row 2 hasn't been replaced before I do that second step, so nobody can get mad at me. All right, row 2 plus row 3. I'm breaking my own rule. I'm going to do that in my head and replace row 2. So row 2 plus row 3 is going to be a 0. 4 plus 2 is 6. Negative 3 plus 2 is a negative 1. And then I'm going to get a 0, 1, 1. Now I'm going to write down the busy work for the second one. Row 1 is 2, negative 1, 1, 1, 0, 0. Double row 3 is negative 2, 4, 4, 0, 0, 2. Combine, I get 0, 3, 5, 1, 0, 2. 0, 3, 5, 1, 0, 2. Row 1 stays the same. When I get two zeros in the same column, now I have a 2 by 2 to solve. Once I get this done, I can use these two guys that'll be left to get zeros here. Make it really, really easy. All right, next step. I need to get a 0 where that 3 is. So I'm going to have row 2 minus twice row 3 and replace row 3. And I'm going to write down my busy work here. Row 2 stays the same. Negative 2 times row 3 gives me minus 6, minus 10, minus 2, 0, minus 4. Combine, 0, 0, negative 11, negative 2, 1, negative 3. That's my new row 3. Rows 1 and 2 stayed the same. Copy carefully. Now my new row 3 is 0, 0, negative 11, negative 2, 1, negative 3. Now I'm going to use that negative 11. The book will tell you to divide it out and get a 1, and that's fine. You know what? Let's do what the book says. I'm going to say row 3 divided by a negative 11, replace row 3. And I'm also very soon going to run out of room. 0, 6, minus 1, 0, 1, 1, 0, 0, 1, 2 over 11, minus 1 over 11, I'm going to have to deal with fractions, positive 3 over 11. I'm going to use that 1. I'm going to say row 2 plus row 1, row 3, replace row 2. And I'm going to say minus row 1 plus row 3, replace row 1. All right, the first one's easy. I'm not going to write down the busy work, but you really should because you've got denominators to deal with. Row 2 plus row 3, replace row 2. 0 and 0, 6 and 0, minus 1 plus 1. Okay, now being very careful. This is 0, this is 11, 11, and 11, 11. So when I'm adding these guys, I'm going to get 2 over 11, 11 minus 1, and 11 plus 3, all over 11 here. Sorry, doing things in my head. 11 minus 1 is 10, and 11 plus 3 is 14. And I'm going to have to divide that by 6, but you see that all three of those numerators are even, so I'm going to end up dividing by 2 on the top and multiplying by 3 on the bottom, and it's not going to be all that bad. 0, hold on a second, 0, 0, 1, 2 over 11 minus 1 over 11, 3 over 11. Row 1 stayed the same, except I'm going to do this next little process here. Negative row 1 would be minus 2 plus 1 minus 1. Negative 1, 0, 0. Row 3 was 0, 0, 1. 2 over 11. Negative 1 over 11. 3 over 11. Now you know why I don't do it this way, and I just get common multiples and then divide at the end. All right, negative 11 plus 2 is negative 9 over 11. 0 plus negative 1 over 11. 0 plus 3 over 11. That's my new row 1 minus 9 minus 1 and positive 3 over 11. Okay, I'm running out of room. So all I have left to do is to make this a 1 and use it to get a 0 here. That's going to require some division. I already have common denominators. I'm going to need to get a little bit farther common denominators, but we'll be all right. Okay, so writing very small, which is hard for me. I'm going to divide row 2 by 6. I'm just going to write this here and replace row 2. That's going to make that a 1. And then after I've done that, I'm going to say minus row 1 plus row 2, replace row 2, and then I'm going to want to divide that by negative 2 and replace row 1. Oh, that's, sorry, replacing the wrong rows here. That's row 1. Replace row 1 and then divide out the negative 2. All right, doing all of that at once is going to be fun, and then I'll just erase something so I have room, and then I'll write down my answer. So row 3 is what it is. This is 2 elevenths minus 1 11th, 3 11ths. Row 2 is going to get divided by 6, which is going to give me 0 1 0. Dividing 2 over 11 by 6 is dividing the top by 2, which gives me a 1, and dividing the bottom by 3, which is going to be 1 over 33. Sorry about that. Dividing 10 by 2 and dividing the whole thing by 3 multiplies the bottom. Same thing here. I get 7 over 33. Okay, using what I just did and having a negative row 1, I'm going to make my little notes over on the right hand side. So minus row 1 is 2, negative 1, 0. Positive, all of these are over 11. So positive 9, positive 1, and a negative 3. And using the new row 2, I've got everybody's over 33, which means I have to get a common denominator. And I have a 1 and a 5 and a 7 with a 0 1 0 over here. So when I combine those guys, the left hand side is going to be 2 minus 2 0 0 augmented with, now remember, getting a common denominator means all of these guys are going to be multiplied by 3 before I combine them. So I'm going to have 18 times, I'm sorry, 3 times 9 is 27, isn't it? Was yesterday anyway. I'm going to have 27 plus 1 is 28, and everybody's over 33. 3 times 1 plus 5 is 3, and 5 is 8. And 3 times negative 3 is negative 9, plus 7 is negative 2. Now, let's not forget that we have to divide this thing by 2. So dividing by 2, my new row 1 is going to be 14 over 33, 4 over 33, and negative 1 over 33. So 1 0 0, copying that down. Now notice that the bottom row is over 11. Everything else is over 33. So if I'm going to factor out the denominator, I'm going to have to multiply the bottom row by 3 over 3 first. And I'm going to get A inverse is 1 over 33 times the matrix, doing the bottom first, multiplying everybody by 3. And now if you look and distribute that 1 over 33, the 3's will cancel and you'll get what we had before, and the denominator will be 11. Everybody else already has 33 in the denominator. 14 and a 4 and a negative 1. Now we take that inverse. We want to solve for the x matrix, right? That'll be x1, x2, x3. And the way we do that is we take our inverse with the fraction conveniently pulled out, and we multiply by that b, the parameters on the right-hand side of the equal sign. And when we get this matrix multiplication done, we'll have equivalent matrices. The x1, x2, x3 will equal this column matrix that we end up with, and we will have solved for our variables. I'm going to give myself a little room here with an eraser. We've done all this work. I'm telling you, don't erase on your paper. Always just get a new piece of paper. And don't write too small. You need to write big enough that you can see what you're doing. And you need to keep everything lined up straight. Straight rows, straight columns. Make sure it's all lined up instead of being messy like me. Okay, performing the multiplication here. I'm going to get the 1 over 33. Now, when I do this, 14 times negative 1, 4 times 5, positive 20, negative 1 times 8, putting those guys together, I get 6 minus 8 is negative 2. Row 2 down the column, I get minus 1, positive 25, positive 56, that's ugly. 70, 81 minus 1 is 80. Last row, 6 times negative 1, negative 3 times 5, and 9 times 8 is 72, positive. So 6 and 15 is negative 21. Subtracted from 72 gives me 51. So equating this matrix with this matrix, I have my answers. I'm going to write these up here at the top where I have room. X1 came out to be negative 2 over 33. X2 was 80 over 33. And X3 is 51 over 33. Checking your work by plugging those into the original equation looks like it's going to be god-awful, but you have a common denominator. And because you have a common denominator, that makes it easy. Once you get your answer on the left-hand side, when you divide out the 33, you'll see that you get the negative 1, the 5, and the 8. Always check your work. There's never any excuse for getting anything wrong when you're solving a system of equations. All right, there you go. And again, the homework from this section was 1 through 25 and 41 through 47, all the odds. And this is section 2.3. And there's your homework. Have fun, guys.